Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. How do you prove the correctness of services that underpin a huge portion of the internet? At the scale of Amazon Web Services, traditional testing doesn't always quite hit the mark. In this episode, our own Will Wilson and Ben Collins talk with Marc Brooker, a distinguished engineer who has spent nearly 17 years building core infrastructure at AWS like S3, Lambda, and Aurora. Marc gives us the inside story on AWS's decade-long journey from formal methods to lighter-weight approaches that any engineering team can adopt. He shares his counterintuitive lesson that investing in correctness doesn't always trade off against development velocity. And we also talk through what role AI will play in the future of programming and verification. If that sounds interesting to you, stick around.
Cool. Welcome to the Bug Bash podcast, everybody. Today we have an extremely special celebrity guest. It's Marc Brooker from Amazon Web Services.
Hey, Marc. Welcome.
Hey. Well, thank you. This is super. I'm super excited to talk to you all. Big fan of what you all are doing, and going to be a good conversation.
We are also big fans of what you are doing. We use Amazon every day. In fact, we use it roughly every microsecond.
Good. That's what I like to hear.
Right, and I think some services you helped build too, right? Some pretty gnarly things that everyone relies on.
Yeah, tons of interesting systems fun over my almost 16 years here at AWS.
So, for our guests who don't know exactly what it is you do, can you just briefly explain what your role is at Amazon and how it all works?
Yeah, so I'm an engineer here at Amazon. I've been at Amazon and actually at AWS specifically since 2008. Spent a bunch of time on EC2, sort of in the early days of that cloud business when people were still asking, why would I buy a computer from a bookshop? What is this cloud thing? It's gotten a little bit out of hand since then, and so I spent some time on storage. And then joined the Lambda team around the time that product was first announced, and spent 5 years working on serverless compute and a whole bunch of AWS's serverless offerings. And then moved into the database world. We built Aurora Serverless and then Aurora DSQL, so these two pretty new, big-scale serverless databases. And then over the last 18 months or so, I've been focused in the AI world on infrastructure for large language models and infrastructure for agents, infrastructure for generative AI, and this kind of second act that serverless is having with agents and some new ways of developing.
That's super cool. I think the way this particular interaction came about was that we saw the really fantastic white paper that you and Ankush wrote for the ACM, all about sort of Amazon's testing practices in-house, how you guys are using formal methods, how you guys are using what you call lightweight formal methods, although it wasn't totally clear to me how lightweight formal methods are different from just good testing.
Yeah.
Yeah, I mean, do you want to talk a little bit about that paper?
Yeah, so we actually there's a whole lot of history there. Back 2014, maybe a little bit before that, I was working in storage, and we were using a lot of TLA plus and a couple of other techniques of these formal techniques, and we got talking to Leslie Lamport at the time. Me and Chris and a couple of other folks from AWS got talking to Leslie Lamport, and he said, well, hey, it would be really great if you guys could write up for something like CACM the ways that you are using TLA plus and how you're using formal methods at AWS in reality rather than as this academic thing. And so we wrote an article. Mostly Chris led the writing of that, Chris Newcomb. And Leslie wrote a great sort of introduction for that in CACM. And so that was 2015. And then late last year, the editors of CACM reached out and said, hey, it's been a decade. This paper was pretty popular. How about talking about what's changed since then? And obviously that was super exciting because we've done a lot more in the formal space since then, and wanted to tell a bigger story about our testing practices and correctness practices and how we're thinking about that end to end. And so, Ankush and I ended up writing that and combining all the work that he's been doing with P with the bigger picture of testing stuff, and then the lightweight things that folks here like James Bornholt have been leading the charge on, and trying to really kind of do more of a broad survey than we did a decade ago.
If I want to follow up on that kind of change over time, right? You said a decade ago it was more TLA plus, now lightweight. I mean, what do you think really motivated that shift for you?
I think getting more adoption was really the big driver, right? We were using TLA plus in a lot of our businesses in 2015 and earlier, sort of starting 2010 or so, but the total number of people who were writing TLA plus, even at a company like AWS, was quite small. It was hard to get the average engineer kind of into that TLA plus mental model because it's weird. It's a very different way of thinking about the world. And so we started to think about, hey, there's so much power in these techniques. How do we bring them to a broader range of, developers, a broader range of non-developers, a broader range of scientists, and so that was one big evolution. And then the other big evolution was, we hired a bunch of people whose actual day job it is to think about formal methods and automated reasoning, and they helped with bringing in these tools like P, bringing in some of the formal tools that we use to check threading, and the tools that do the kind of lower level kind of code verification things. And so it was a bit of a journey up. How do we make this more popular? Bring in more people, bring in more developers, make it something that a larger range of our engineering teams feel like they could use, and at the same time broaden that practice from just being focused on distributed systems and protocols to also authentication, device simulation, virtualization, like these really low-level things that, as a cloud provider, we just have to get right.
So I want to preface this question by saying I love formal methods, and I think the world would be a much, much better place if more people use them. The thing I've always wondered is, I think formal methods are very powerful if there's a pretty easy or obvious translation from the specification to the actual implementation in real code. Mm-hmm. But if you have a domain where that mapping is not easy, right, because the real implementation needs to be highly optimized, let's say, then there's room for bugs to creep in when the implementation diverges from the spec. And so, how do you guys think about that challenge? Do you have a pretty principled way of solving it? Do you just find it's not a big deal in practice? What's your thinking?
Well, it's a huge deal in practice. I think a lot of formal methods people are a little bit defensive about it, saying, "Oh, well, But I think about it in three ways. One of them is doing that formal specification and model checking is useful even if there are bugs in the code, right? Even if bugs creep in between that model checking step and the code implementation step, we've still found we get a huge amount of value out of that. And so, it's not as big as kind of gotcha as some folks sort of approach it as. Another one is, as we've broadened our practice to include things like what we're doing with Carney and what we're doing with Daphne and those sort of more kind of code level tools, those are ones where we're using automated reasoning techniques, formal modeling techniques directly on the final implementation code. And so that it's harder, it's more work, it's harder to do the big picture stuff, but it does very effectively close that gap and say, we're actually checking the implementation. Now, there's still assumptions. There's still assumptions that the CPU is bug-free. There's still, those kinds of assumptions. And so you can get a little bit sort of existential about these things. But in practice, again, we've gotten rid of one major way that bugs can creep in.
So, I want to ask, you describe formal methods and lightweight formal methods. In your experience, like what are the applications? Like how do you judge which kind of application is going to be best for which type of testing? Like it almost sounds like there's a gradation of approaches, right? And so like how could someone pattern match just be like, oh yeah, this is the sort of thing, Mark would use. Well, you should use for this type or this type.
That's I think that's a great question, and in some sense, I think there's a fairly clear reductive answer to that of saying, hey, if you're writing these programs that are focused on relatively small, relatively local properties, something like virtualization, device emulation, those things have a specification that's, honestly very small. The implementations are very small, but they're super high value. And that's where I've found using the, code level tools have been super, super helpful. Similarly with things like authorization, right? Like one of our teams built this thing, CEDA, which is a formally verified authorization policy language. With a formally verified compiler and those sorts of things. And again, it's checking these local properties. They're super important that you get them exactly crisply right. And then at the other end are these big distributed systems, right? And so you're building things like Lambda or Aurora DSQL or S3 or whatever. And they tend to be questions about distributed protocols, questions about behavior under failures, questions about behavior under reordering, and so on. And that's where the P and TLA plus level of techniques fit in. I think there is a little bit of an awkward middle between those two things where we don't quite yet have the right tools to stretch between them.
Right.
And that's one place I'm really excited about. Yeah.
Because you sort of say, hey, the bigger the system, the more spread out, actually the more formal we're going to do the proof, right? I mean, I'm almost tracking that, right?
Yeah, I think the more value we get out of these really critical safety and liveness properties at the distributed protocol level, right? And so if I think about, I'm going to build my entire house on a variant of Paxos, and I better get that variant right because everything else depends on the core correctness of that protocol. And I think that's where there's just this massive leverage in getting those protocols right, getting those designs right, because you can then use the invariance you get from that to design and build all of the other pieces of the system.
Something that Ankush said in his Bug Bash talk, which I really thought was spot on, was that so much of the value of these techniques, whether it's formal methods or it's just property-based testing, is that they really force you to think about what your program is supposed to do.
Yeah.
Which sounds like a very small thing, but which I suspect is a thing that's rarely done in practice, right? Like when you're writing the properties for some function or you're writing down some invariant, you have to actually ask yourself, what is this meant to do? And sometimes just asking yourself that question causes you to find bugs before you even run the checker.
Mm-hmm.
So in my cynical heart, though, I suspect that actually a lot of the resistance to using these methods basically comes down to people don't like to think very hard. Like what do you think?
Don't want to pre-plan or something, right? Like I don't want to like decide up front everything that's going to be true and false about this system,
right. So my question for Mark is, like, as somebody who's rolled this out at like a very big company, like, do you think there's hope of overcoming that resistance? Is there some way that we can make the UX of using these tools so smooth, or maybe where we can incorporate it in the design process or something, such that people are willing to undergo that short-term pain?
Yeah. That's a great question. And I do think that's part of the resistance. And, on the lightweight side, just the benefit of doing something as simple as draw your state machine on a whiteboard, right, is huge. It's a relatively small amount of effort, and just being that explicit is massive. But to really sort of get into your question, like, how do you get to that point? One of them is to make the tools a lot easier and to reduce the barrier of entry of the tools. And I think one of the places where, if you listen to what Leslie Lamport's been saying since the 70s, he's had this very mathematical framework, but it's always been about what are the benefits of doing that upfront thinking, and how does that lead to quality? And so he's chosen this one tool of TLA to do that, which has turned out to be great, but a lot of people find the mental model of that hard to learn. And so I think one of the great things about P and the work that Ankush has done there is it's much easier to approach as for most programmers, both as a mental model and just as a syntax. And that helps. And so I think, big step number one is just getting the tools right, getting the tools simple, getting the mental models right to match what developers have. And then the other is, helping people understand the value. And I think one of the cultural benefits we've had at AWS is the same teams at AWS run our services as built them. It's the same folks on call, right? We don't have operations teams for the most part. We don't have separate SRE organizations. And so people very viscerally feel like, hey, if I get this right, my page is not going to go off. And so, getting that connection between the value and the work, I think is a lot more visceral in our style of culture than maybe in some other places in the industry, and that helps. And it's a combination of those two things. Like, why should I bother with this? Why is it not just drag? And how can I lower that barrier to entry and lower the cost and lower the conceptual complexity? And then the third part of the story, and this is something that Ankush talks about a lot, and a bunch of folks talk about a lot, is we've found that it actually makes development faster. We found that it reduces debugging time. We found that it reduces rebuilding time. And we found that it reduces kind of operational pain to the point that our teams are delivering faster. And so you have to get people over that hump of, it feels like more effort, but it actually might be less effort at the end of the day.
Yeah, this is something that Ben can probably speak even more to than me, but like at Foundation DB, like the part of that whole story that I think people find hardest to believe, but which, if anything, I understate sometimes, is just how much DST contributed to our velocity. Like, we built a freaking distributed database with excellent fault tolerance, top-notch performance, and fully serializable interactive ACID transactions with like a team of like 8 people, like very quickly. It's like that's just so crazy. And then we rewrote it to make it faster, which is like another crazy thing, right? Like, who does that? And if we had not had these techniques at our disposal, it would have taken us 1,000 times as long if we could have done it at all.
Right. No, it was a lot of fun to work on. And I mean, honestly, right, that's like why we're doing Antithesis. Like, we saw the light, right? And we lived in this world where we had this amazing testing framework and could work really fast and really gracefully there. So, yeah. Now, in the numbers of different like testing scenarios that you talked about, we're testing tools, testing regimes, Mark, do you see DST being used at Amazon today? I mean, we talked about lightweight formal methods. I mean, DST sits like aside those things, right?
Yeah, and I do. We use DST techniques, maybe not as sophisticated as the ones that you all offer. All over our systems, and probably DSQL is the one where we've done it most end to end, and a lot of that is. Some of it's about correctness, but a lot of it is about improving development velocity, right? If you can find those bugs at build time, if you can find those bugs in your IDE and meaningfully test distributed systems properties inside that kind of inner loop of development, the velocity is so much higher than discovering those bugs, even 12 hours down the line when you get into your first layer of end-to-end integration testing.
Yeah, let alone when a customer reports it 3 months later and you've completely forgotten what the code does.
Right, yeah.
Right, and we had this great thing when we were at FDB. We could, as we were just coding, kick off these tests and, wait for the first 10 reports and you're like, if nothing failed there, okay. And that was within seconds, right? And then maybe wait for the next 100. And if, maybe that was okay, and if it was in the middle of the day and you're like, okay, that's good enough for me. Like, I'm going to go, do my next task. Then you just kill it off and go to the next thing. Right. And it was like, I think also the other thing is like the way that compute allows that to expand, right? And sort of like give you more confidence as you spend more CPU cycles on it, I think is another totally like next level mindset shift with the confidence that type of approach can give you.
Yeah, I mean, I really like that too. And, ultimately this whole field is about incrementally building that kind of confidence. And if you can make that very immediate of, here's the number of cycles I'm going to invest versus my level of confidence, that really helps. Really helps people reason about it and know, how much effort you should be spending on it and where you should be spending that effort at different parts of your development life cycle.
So, can I ask a little bit about the history of DST at Amazon? As near as I can tell, there were actually 3 different teams which all began experimenting with this style of development at around the same time. I think at FoundationDB, we started doing it in around 2010. Does that sound right, Ben?
Yeah, 2010, definitely.
With some precursors in some of the performance simulation work that Dave had done at Visual Sciences back in the early 2000s. And then I think at Google, Chubby, which is their distributed lock manager, experimented with DST a little bit at right around the same time. And then I think, Mark, you were saying that at Amazon, you guys were also experimenting with these kinds of ideas at around the same time.
Almost exactly the same time, which is just super interesting. El Vermeulen was one of the early, engineers at AWS. He was the CTO of Amazon for several years and realized he didn't like that CTO of Amazon role as much as he liked being a software developer. And so, joined the S3 or kicked off the S3 team in the early days of AWS and has been super influential. And really around that time was the first time, I think I've seen L's writings about, using those kinds of techniques, using these DST techniques to test things in S3. Around that time, he was building a honestly very chubby shaped lock service called Alf, a little bit more ambitious maybe. And that was entirely kind of DST based. And then started really kind of pushing those techniques into other teams. We started picking them up in the storage organization. And so it's just super interesting that there was this convergent evolution of testing techniques and different people thinking in similar ways, maybe not exactly the same way about that.
Right. Well, it's like calculus, right? You don't have it for thousands and thousands of years, and then Newton and Leibniz develop it practically simultaneously. Sometimes an idea's time has just come.
Yeah. And, I that's my best guess for what, why there's so much evolution here. Is it was just such a great idea and its time had come.
That's really cool. Can you, what do you think about, what was your experience with sort of the human factors of trying to get people to use DST? Was it hard to convince them to see the benefits? Was it, presumably you guys, if you wanted to test a system in this way, that system had some relatively harsh requirements on it, had to have a particular threading model, probably had to, not have a whole ton of dependencies. Were those challenging things to get teams to go with?
I mean, I think doing the actual work is always challenging, right? Folks are busy, teams are busy, they've got a lot to do, they've got a lot on their plate, and saying, well, you've got to stab out every time you use time, every time you do I/O, every time you use a random number, like all of these different things, and wrap them up in a certain way. And especially in the early days, we didn't have really good ergonomics around that. So it was a bunch of lifting. But on the other side, I think, software developers really got it early, right? Like, I think folks just really did like this. I'm still in my IDE. Probably in those days it was, I don't remember. I was probably using Eclipse. I can click build, I can click test, and I'm meaningfully testing these distributed system properties.
Right. And anyway, you get to almost pretend like time is rational and like the network is rational and disks are rational. And so like as an engineer, you're like, okay, great. Like that would be a wonderful abstraction, right?
It's a nice fantasy world to live in. For sure.
So right. It's like both harsher and a wonderfully like organized fantasy world. Yeah.
And so in some sense, people get it immediately, and then you're like, well, it's more work, and everyone's like, well, I'm not looking for more work right now. So two sides of that, and I think what was nice with DSQL and with some of the projects that preceded it is we got to build that way from the beginning rather than trying to retrofit into an existing code base.
And that was one thing we found on FDB. Was we started with that at the very beginning, right? Our co-founder, Dave, this was like, from the very beginning, his like vision about how this would get tested. And we hit some snags along the way in terms of integrating with external systems. We tried to have Zookeeper as an external system. And inside this is one of the early successes. I don't know, Will, were you around already by then, or was this predated?
Yeah, but I've heard this story.
Yeah. So like we stubbed it out for the DST. And we tried to give it the worst contract we could imagine, right? Because you want to make things as bad as possible. And we got the early Foundation DB system doing this, consensus with Zookeeper. And then we decided, okay, it's time. We're going to install it on some real computers with a power switch that we were going to go, switch on and off to actually turn these things on and off. And instantly, Zookeeper was on the floor. Instantly. And so we had spent all this time mocking it out and creating this like very complicated system to do so. And so then, this is one of the refactors we were talking about. We're like, okay, well, I guess now we're going to be writing Paxos. Like, so, and in fact, I don't remember if it was like 3 weeks or 4 weeks. It was unbelievable, or maybe 5 weeks. It was an unbelievably short amount of time to write a Paxos implementation that we subsequently had 0 bugs ever in. Like, really, truly amazing, right? So obviously the hindsight there was like, wow, we should not make that mistake again. And I will say I'd love your input on this, Mark. Like, it pushed us into a world where it was actually pretty tricky to have external dependencies, both because they didn't fit in the low latency DST, but also because it was hard to envision all of the failure modes that those systems might have, right? So they tend to get you into this, we call it a fantasy world, kind of trying to get you into this fantasy world where it's hard to have these external dependencies. So I don't know. Maybe this is why some of the formal methods and sort of speccing things out helps in this area.
Yeah, and thinking about those contracts. But I think it does make it hard, to have external dependencies. It does make you much more thoughtful about what contract you're really expecting from those external dependencies and how you're checking that contract. And I had what sounds like a fairly similar experience with Zookeeper and a fairly similar journey where we decided to end up doing some of that ourselves. But yeah, it certainly has, I think, given a team a sort of healthy approach to taking on external dependencies for these really core functions. And if I think about something like database replication and transactions, it's hard to get more core than that. And so that's somewhere where having the correctness argument being end to end rather than being, well, then we depend on this other component to do this thing, has such value.
So I'm a little curious. This is a slight change of subject, but you mentioned before, DSQL and some of the new features of S3. Something that's consistently impressed me about AWS is how you've tended to roll out, groundbreaking, industry-changing new capabilities in a relatively scrappy, rapid way, right? Like when S3 was first released, it did not have strong consistency guarantees. And then you came and added it. And that's very hard to do. Like, I don't know how many of our listeners have tried to add an invariant like that to an already very large, very mature system like S3. but it's not easy.
Yeah.
Any secrets you can share about how you guys have done this several times in a row so successfully?
Yeah, and I'll admit I was only very peripherally related with that S3 project, but I do, really admire the work that the team did there. And it's harder than it looks doing that kind of work. And one of the reasons is, S3 has a very simple API, but a very complicated set of expectations in customers' heads for what it means to implement that API in terms of performance, behavior, failure modes, all of these other things, these sort of implicit requirements. And the team had to set this really high bar for not kind of breaking those things, right? You can't regress on performance. You can't regress on failure, and actually they wanted to improve a lot of those things. And I think what works there and what's required there is finding the right balance between being extremely humble about how hard the problem is and just extremely bold about, like, we're going to go and take this on. We're going to figure it out. We can do this. We know how to do it. And so it's constantly this tightrope walk of we've got to recognize how hard this is going to be, but we need to really believe in our ability to do that. And then investing in testing, investing in formal methods, investing in verification and these pieces, and then investing in a lot of tooling to do incremental rollout in production, investing in very low risk rollback, investing in a lot of runtime monitoring so you know that stuff is working in production. Things like we talk about p-observe in the ACM paper, and I think it is, maybe if I'm going to pick on one core thing, it is that being able to roll forward and roll back and making that low risk and really investing in making that incremental and low risk. And so we're going to start a little bit of traffic. We're going to start a few customers. We're going to start some internal workloads. We're going to really monitor those. First sign of trouble, zero impact rollback to the old system, and then you've got a little bit of breathing room.
It's one of our most common customer use cases, actually, is people, who want us to test roll forward, roll back under sort of arbitrary network conditions and fuzz over what could happen during a roll forward or roll back.
Yeah, aren't these like multiple versions and kind of advancing and regressing? That's actually, I thought, in my experience, this was at Foundation EB, that was actually one of the hardest things to test the multiple versions against each other, right? Because it's one thing to test a version of your software against itself, and it's another thing to test multiple versions, sort of forward and backwards, that make sure those things work together in concert. It's a very high bar. I admire it, but it's tricky to achieve. And I don't know, do you have any additional ideas about that particular constraint and how you test for that?
Yeah, it is a difficult thing to test for sure. And I think one of the ways that we have used, these simulation techniques is to be able to do a lot of that testing of behavior changes at build time. I think one of the other ways is to be very thoughtful about how rich you make the contracts. And so if you think about a really general model like a distributed state machine, that is depending on every replica, in that sort of typical Paxos model, every replica applying operations exactly the same way, bit for bit. And so anything you do that changes that behavior becomes really hard to roll out and even harder to roll back, because you've got to now do this atomically and it's got to be built into the protocol. And so there's a whole bunch of things. And so if you're going to expose that kind of richness, you've made your life very difficult. And so there's also this kind of API design thing of saying, well, maybe I don't want to expose an arbitrary state machine. Maybe what I need here is a check and set register, just bit match, right. Very simple contract. And now I've got a much easier place to stand when I think about validating that the roll forward and roll back works, because the contract is just a ton simpler. that's great until you get into SQL databases or databases generally that tend to have these very rich contracts with their clients, and that becomes hard. But even there, it's a case of how much of can we simplify what bytes end up on disk contract away from the very rich, here I'm executing SQL and I have hundreds of types and I have arbitrary programmability and arbitrary interactions with clients and all the difficulty that comes with that. And then maybe the last one, one of the things that we did a lot with DSQL was this differential fuzz testing, right? Like we would take just standard Postgres running on RDS. We would take DSQL and we would generate SQL, tons and tons of SQL, and run them on both and check that the results were the same. And that was a compute expensive technique, but just massively useful for bug finding.
Yeah, there was a good article on Hacker News the other day about how any kind of fuzz testing or property-based testing is just completely overpowered when it comes to migrations or, upgrade in place or anything where you have, a reference implementation as a test oracle. Because one of the hardest things about property-based testing is knowing, have I found a bug or not? And if you have something where you can check against it and be like, did this give exactly the same answer? That problem just gets massively, massively simpler. And these techniques work so well.
Yeah. Yeah. Just having it is an incredibly overpowered and useful technique.
The slight extension to it, which I've tried to convince people also works pretty well, is if you have a very complicated system that you're testing with a relatively simple interface, right? For example, something like S3, like you're putting and you're getting files and you're listing directory contents and so on. It just needs to be incredibly scalable, incredibly performant, incredibly reliable. You can still do this like sort of Oracle style fuzz testing with a very, very simple model of that system that you build, which has no strict performance guarantees or whatever. And often that model, like it sounds like a lot of work, like, oh my God, you're asking me to make a second copy of my system, but I'm not. Like that model can be like a one file Python program often, right? It can be much simpler so long as it expresses the same semantics as your other system.
Yeah. And I think, I could open Cursor or something and vibe code something that implements the S3 API in, half an hour. Right,
Yep.
It's not going to be scalable, but it's going to implement exactly the same API because that API is simple. And there's so much value in designing systems to have those kinds of properties because it makes life so much easier.
So speaking of vibe coding, what do you think of AI coding, and what do you think it means for testing systems correctness, verification, all that stuff?
Yeah, I'm actually super optimistic about that. I'm a big AI fan. Obviously, that's my day job, so I've got a little bit of bias there. But I use those tools every day. I don't really love this vibe coding kind of prompt by prompt pattern. I don't find it particularly repeatable. But I do think that there is a moment that is happening with realizing that really what we're doing is we are up-leveling programming from being more of an implementation task, especially with the kinds of imperative languages we use day to day, into being more of a specification task. And the core challenge with vibe coding is that a bunch of disconnected prompts in natural languages doesn't make a good specification. It's just not a good channel. And so, I think where I see the space going for, AI-powered programming is finding better ways to build those specifications that are both, ergonomic and understandable for humans and ergonomic and understandable for models. Then, building the tools that interact with those specifications and building the tools that translate those specifications into programs, and then validate that the programs implement the specification. And I think what we're seeing in the industry is just really kind of the beginning of a big transformation in that direction.
Doesn't this take us back to one of the very first things we were talking about, though, is that specification is hard and people don't usually do it, et cetera? Is this some like full circle thing? Like, how do you see this relating, Marc?
I mean, it is. It's exactly that, right? Like it's suddenly the tool is requiring me to write down what I mean pretty precisely. And sometimes that's awkward and sometimes it's hard. And it's really easy to type, the wrong thing into Cursor and QCLI, and it gives you the wrong output, and you're like, AI. It's but really, I think as the models have become more sophisticated, it has become closer and closer to, can you precisely describe what you're actually looking for and what you mean, at least the parts of that really matter. And that is hard. And I don't think we've got, as an industry, the ergonomics of those tools right yet. And I think even a lot of programmers, if you say this word specification, it sounds a lot scarier than it really is. And a lot harder than it really is, right? Like saying, hey, what we're really trying to do is write down precisely what we're trying to achieve and what's important about that. And then it becomes much closer to the sort of core mental work of software development.
So the obvious question this raises then, right, is can you write down the specification once and use it both for program synthesis and for verification?
I sure hope so. Yeah, because otherwise you end up with this I have two specifications I have to keep in sync problem, and that's always going to be difficult.
Do you know of people either in formal methods or in property-based testing who are trying to go at this very directly, who are trying to sort of create that unified experience?
Yeah, I mean, I don't think they're very directly. I think everyone's kind of iterating towards it, one way or another, and that's interesting to watch. But I haven't seen anybody really tackle it head on yet, especially in the sort of formal world of saying, what would a higher level but still crisp enough specification language look like?
Mm-hmm.
And I think there's going to be this kind of COBOL moment at some point where somebody figures out that recipe and then everyone's like, wow, this is the beginning of a big and long journey of a new way of doing software.
So a year and a half or so ago, 2 years ago, I was in Cape Town to visit, I think, a mutual acquaintance of ours, Joran, at Tiger Beetle, for his Systems Distributed conference. And I learned there that EC2 actually came out of Cape Town. Right?
Yeah.
Amazon had a Cape Town office, and I guess a lot of the people involved were from the University of Cape Town, which I think was your alma mater, if I'm not mistaken.
Yep, that's right. EC2 still does have a big office in Cape Town. A huge amount of the sort of core work of EC2 and some other pieces of AWS, happen there. EC2 started in a small office, about 10 minutes drive from the university. A bunch of UCT people, a bunch of other South Africans, and some people who had come from Amazon in here in Seattle and spent a bunch of time in Cape Town, and it was just such a great team. I think I joined that team. I was about the 10th-ish person,
so
maybe a little bit more than that.
There in Cape Town on that team.
Yeah.
Oh, okay.
I worked
Nice.
there for about 4 years on that team.
I was pretty stunned by the size and sophistication of the Cape Town startup scene and tech scene. There's a lot going on there.
There's a lot of exciting stuff, going on there, and I'm just it's great to see it. Obviously, a huge fan of what you're on and the Beetle folks are doing. They're on a tough journey. I think being a niche database vendor is a hard lifestyle, and
Yes.
I really hope that it turns out great for them. But the technical work they've been doing there, and the testing work, and the communication and go-to-market work is really, just super admirable. And it's a great scene. There's so much energy in tech and other startups down there, and very, very exciting to see. And actually, across the whole continent, there's just a ton of innovation going on with a lot less resources than maybe what startups here and in the west coast of the US can enjoy.
I was pretty stunned when I arrived. I didn't know what to expect. I was not expecting, one of the most beautiful cities on earth with a Mediterranean climate and a thriving Amazon office. It was like incredible. It sounds like a very nice place to work.
A special place and a very, very fun town to go to university into.
Cool. What else should we talk about?
Well, I'm obviously always super interested in hearing about, how you all are thinking about formal methods. And I don't know if you want to discuss this, but one thing that I've been, very interested in your vision for DST is how you can use formal methods and automated reasoning to really get great coverage and reason about how much coverage you're actually getting. You sort of talked about this, we're going to do more testing and get more confidence. And I like that as a mental model. But there's also this more formal way of saying, it's this multidimensional space and we want to explore it in a principled way. And I'd be super interested in hearing how, you and Will and Ben are thinking about that.
Sure. So I think when we think about how we are covering a program's state space, that is a very, very challenging problem to solve in full generality. So our internal jargon for this is the problem of strategy. Because if you know that you have reached a certain new and distinct part of the program state space, that both gives you confidence, right, that you've covered some important behavior, but it has this dual function because it also can be a very useful incremental point for doing more exploration, right? It lets you guide the discovery a little bit rather than just doing totally random fuzzing. Like this was the great breakthrough of coverage guided fuzzers like AFL. It turns out that I've reached a new line of code in my parser is both like good because I now know I've reached that line of code in my parser, but also it helps me get deeper into the parser, right? And if I can take the input that got to that line of code and then mutate it or extend it, it can get me a great deal further indeed. So we view coverage in this dual way as well. The thing is that for generalized programs, which are not just parsers or command line utilities or other traditional fuzzing targets, simple code coverage is actually a remarkably bad heuristic for how effectively you've covered the state space. And this is something that we have to do quite a lot of work to, sort of deprogram our customers sometimes if they come from a very coverage-focused mindset. In a distributed system, the order in which particular lines of code have run on different nodes in the system can be much more important than the raw coverage. And then, other more general systems, often like data is far more important than simple coverage. If you imagine you're trying to fuzz a Python interpreter, you could make every line of code in that interpreter run at some point and be nowhere close to exhausting its behavior. And if you think about fuzzing a simple computer game, right, like Super Mario Brothers, you turn the game on and pretty much all the code runs. And then, but you're nowhere close to having explored that whole game, right? And so there's a lot of relatively ambitious things, actually approaches from AI that we're trying to use to grapple with this problem, because essentially it's like a very, very, very challenging, dimensional reduction problem. Mm-hmm. But we are not above cheating when we can. And the really great thing about formal methods is it gives you an amazing way to cheat. Because if I can tie the states of my model to the states of my program in some way, then my model actually becomes a guidepost for how I explore and fuzz the system, right? I can say, oh, in the course of doing my DST, in the course of doing my fuzzing, I reached all these different model states. That's A, giving me comfort that I've explored the system somewhat well. But B, reaching model state A may be the key to reaching model state B. And if it took some really complicated series of events to get to model state A, remembering how I got to model state A, and since we have determinism, like using that as a prefix can, exponentially increase the speed with which I get to model state B.
So you mentioned AFL, and this is the very similar mental model, but instead of saying, "Hey, I got to a new line of code," it's, "Hey, I got to a new state in my model in this very sort of abstracted version of my program."
That's right, and this is, I think, not a secret. If it is, we'll edit it out. MongoDB is currently doing a big research project. They have a big formal methods community there, and they're basically trying to prove exactly this, right? That they can give us a specification. I think they're TLA people, not PLang people. They can give us a specification, and then we can tie the actual real execution traces back to the model, and then use the model as guidance for how to fuzz more effectively.
Yeah. I really like that. I think that's a sort of steps towards closing this middle ground between doing very abstract protocol stuff with things like TLA and doing low level code stuff with tools like Carney and Daphne and so on.
Yeah, and the nice thing about it is it also the version of this that I've described is like the very sophisticated version, but you can also do a very stupid version. You can just add log messages at points in your program that are interesting, and then tell us what the format of those log messages are, and we'll use them as incremental strategy points.
Right. If you know in your program that this is interesting state A or B or C, right? Those can be sort of like baked directly into the source. It's not in the same formal way as in a specification, but it actually, the developer often, although maybe they didn't write the specification ahead of time, does know in the end, like, these are important states, right? And so finding the combination of all those things and exploring them is important.
And the really interesting thing about this style, so the generic term that we give for this in our APIs, we call them sometimes assertions. They're basically the dual to traditional assertions, right? Traditional assertions say that this always or never happens. Sometimes assertions say that this can sometimes happen. And they're actually useful beyond just for giving guidance to a testing system. They also give you information about the power of that testing system by, telling you whether you've reached all the states of interest. But then they can also find bugs in your program, right? Like if you accidentally make some state unreachable and you had an assertion that is sometimes reachable, you will now find out. You will get immediate feedback. And, I think property-based testing and DST and so on are sort of uniquely able to find bugs of that form. A traditional integration test or unit test isn't very good at discovering that you have accidentally made some particular state of your program unreachable.
Right.
Yeah, it's almost like what gets omitted. I mean, at the end of the day, Will, some people do just use plain old code coverage for this, right? And, it's like a high noise.
That's right.
Fill in for it, right?
That's right. But code coverage will have a harder time telling me that I've made it impossible to get to a particular location with a particular value in memory, or, to a particular location with a particular history of getting to that location, or whatever, which might be important.
Yeah, and with a particular piece of data.
That's right.
One of the big challenges for us with testing is, we can test code, and then as we roll it out, it starts to get exposed to this kind of data that is arbitrarily chosen by our customers, maybe by some adversaries, and that's a whole problem of its own. And one of the big practical issues there is configuration, right? People come into systems with this mental model of code and configuration are different things, and so I'm going to deploy my code out slowly, and then I'm going to turn everything on with configuration. It's like, no, well, the configuration is new data, and you're just going to find new bugs that way, and really they are, they're not different things.
This was, I think, if I read the postmortem right about the GCP outage from, was it last week? This was exactly the thing. There was a new code path that got turned on in production with a flag. And it hit, some line of code that previously had not been hit.
And probably create some kind of metastable failure, right?
Mm-hmm.
That's another sort of interesting topic. Like, metastable failure conditions are, I think, one of the greatest advertisements for formal methods and for testing, because my goodness, you want to see those not in production.
Yeah. One of the teams here at AWS had a paper at HotOS, a month or so ago about using both simulation, which and then sort of even more abstract than that, using continuous time Markov models to guide the simulation to find these metastable failure states, which is really cool because they're hard to find, right? They tend to be in interesting parts of the state space that it's hard for humans to think, well, what can kick things in there? And so if we can abstract all the way to this kind of Markov model of our system and then use that to pick the bits of the world to explore with simulation, and then use that to pick the bits to explore with, in production testing, there's a great way to get good coverage there. So that was Rebecca Isaacs and Peter Alvaro and a couple of other folks.
Oh, is Peter Alvaro at Amazon now? I didn't know that.
Yeah, Peter's a scholar here, so he's spending I think 20% of his time with us doing fun things with metastable failures right now.
Cool. I liked his paper on lineage-driven fault injection.
Yeah, the LDFI work and Bloom and Daedalus and then Calm. He's had a great record of doing some very cool systems work. As has Joe Hillestein, who's obviously been hugely impactful in the ways that we think about these things.
Mm-hmm. So let me change topics here. I was thinking about this. It was like we've talked about all the success cases. So like, what is a story? I mean, of some place we've tried to do some advanced kind of testing, and in the end we're like, nah, like we're just gonna put some unit tests on that. I don't know, like. Do we ever get to a place where, we bounce off of these techniques? I wonder if there's some lesson to be learned there as well.
I think it tends for us to be the kind of more control plane type things, right? So when you're building a storage system, when you're building a data plane, you're building a replicator, the requirements are very crisp, and so it's quite, I wouldn't say easy, but very tractable to write those specifications and to test them and so on. And then as you get more abstracted into, I'm going to build a control plane, it's going to be launching and terminating things and creating things and taking input from customers. And it's very useful. You can write down those state machines that it goes through, but the implementation just becomes very business logic heavy and very hard to specify and even, crisply. You can crisply think about some things, like this thing must never do this,
right.
It must never terminate more than X percent of instances, right? But the whole state space of what good looks like is really hard to capture. Right. And that's typically where we've struggled.
You can still fuzz it to look for crashes or for really bad behavior, but you're not going to completely pin down, the proper behavior of that system that way.
Yeah, the sort of Kuberneteses of the world, right? Like you can get etcd right, but getting the whole of something like that right is sure is tough, and I don't think is really tractable with the methods that we currently have. But we keep looking. And then the other place, it tends to be the other place for us is UI, and that is where. There is obviously automated, browser level testing. There's a bunch of unit testing, but it's a place where we haven't yet had a lot of success with more sophisticated testing methods.
We actually, internally have a pretty sophisticated autonomous testing system for our UI. And this was we built this a little bit as like a challenge for ourselves. Like, we dream of someday solving this problem for UI as well, but it feels, as you said, very, very scary to do so because there's a lot of complexity there. So we built the system internally to test our own UI, and actually it's worked really well. So I think we are hoping to turn that into a proper product at some point in the future and extend it. There's a couple other examples out there of prior art of people doing this. There's a guy named Oscar Wikström, who I think is now at SourceGraph, but previously he was in business on his own, a consultant. He built a very, very sophisticated, autonomous testing system or browser fuzzing system, whatever you want to call it, for JavaScript apps. Running in the browser, and found all kinds of bugs in every JavaScript framework you can imagine. So I actually think this is an area with some low-hanging fruit potentially. Like, there's a lot of people writing that kind of code, and by and large, they're not that familiar with these techniques.
Yeah.
Right. I mean, we're talking, right, a little bit about up-leveling, because a lot of the techniques we talk about are distributed system people, systems programming people, right? And, like, we're talking about up-leveling that, right? Up the application stack into places that have more business logic, right? It's like messier, right? Like, so I don't know. Maybe some of these tools will, as they mature, move in that direction as well.
Yeah, I hope so, and because that's important.
Right.
It's a huge part of our industry, and it's the kind of it's the face of our products.
Right.
It's the bit that so many people interact with, and and then I think the other, huge unexplored space there are, probably the best part of 1 billion people who, write an Excel formula or macro or whatever, and they don't think of themselves as programmers, but in reality, that's what they're building. They're writing computer programs.
Yeah.
And how should they think about whether those computer programs are right? Because they're making decisions in their businesses and lives with those. And, it's that's a whole space where I think there's a huge opportunity to both simplify that and help people think through, like, hey, is the spreadsheet I built actually giving me the right answer or not?
And those programs are about to get much more complicated with AI.
Yeah.
Right.
Yeah.
Right. It's
Much
going to be
more
much
powerful.
easier, right? Much easier to write a very complicated Excel function.
Yeah, which is great. I mean, I'm always in favor of,
Right.
Exposing the power of computing to more people. I just, that's exciting. But yeah, then those people will realize, oh boy, if I've dug myself into a hole here, how do I fix that? I did want to actually mention p-observe, which is the other bit that, that Ankush and team have been working on. And, this is really interesting, sort of getting to your point about log messages, of saying, we're actually going to take the log traces from an in-production running system like S3. And then from that, we're going to reconstruct the underlying state machine and then check that against the specification to make sure that is a legal flow of states that you can go through in the specification, which is just a super fun additional way to close this gap between formal specification and actual implementation in these systems.
Yeah, now what you guys should do is you should take that real running system and put it into Antithesis, and then we will find you many, many, many more of these execution traces.
Right.
And you can check all of them.
Right.
Yeah. I mean, it's super. Getting that kind of coverage in a pre-production way, I think.
Right.
There's
Maybe
so
that's
much
a
value in.
future idea for us, Will, in the product, is like a p-observe integration, right? That
Oh,
you run your system in there. Maybe Ankush is already working on this. I don't know.
I talked to Ankush about it. He wants to do it. It's a good
great.
idea.
It's
It's basically a race between him and the Mongo people, I think. I think it's going to happen one way or another.
Yeah.
that's amazing.
Yeah, it's super fun, and I think sort of going back to this, how do we close the kind of specification implementation gap? It's a little bit of an out there solution to that problem, but one that has been very practically useful to us, and it also finds some pretty weird things. Like you can find, hey, this machine has bad RAM and it's not actually executing the program as written. Those kinds of bugs, which is super difficult to find with the vast majority of other techniques. Great. Well, thank you. This has been really fun.
Maybe one last thing that we could talk about, just very briefly. We have recently rolled out inside of the antithesis simulation basically a fake or mock copy of AWS or of many of the most common services, because the people who are writing, distributed apps that are designed to run in AWS are sort of the pretty close to the core of our customer base. What do you think we could do in the future to make that integration even more seamless? Like, what could you guys do? What could we do? Like, is this a cool way to go? I don't know.
Yeah, that's really interesting. Like, we have some places like with DynamoDB where we have a fairly sophisticated kind of local development version, and haven't done that very broadly. It's certainly something that we ask, we hear folks ask for is, hey, I want to test things locally. I want to test things in my environment. I want to develop on the plane, back when planes didn't have Wi-Fi. But it's never quite felt yet for us like, hey, this is the one thing that we need to be investing in. Maybe one other way that it seems like we could help is, we publish these API specifications, I think now all in a well-defined computer-readable format with Smithy, but don't have good computer-readable semantic specifications of a lot of AWS. And that seems like something that would be really valuable to client builders, to customers, and to folks who are looking at testing.
Yeah, Marc, thanks for joining us. I mean, it's been great. It's great to hear from, inside the brain trust there at Amazon.
Yes, this was awesome. And thank you once again for giving us bare metal machines and Lambda, without which we could not have a business.
Well, good to hear you're enjoying them. And thanks. It's been super fun to talk to you all. And have a good afternoon.
All right.
Cheers.
Cheers.
Thanks for checking out the Bug Bash podcast. If you want to reach out, maybe with an idea for the show, or maybe you want to be on it, send us an email at bugbash@antithesis.com. Or if chat's more your style, head over to antithesis.com and scroll to the bottom, where you'll find the link to our Discord. Until next time.